We humans have always gazed at the skies to enjoy the various patterns made by the stars and the planets in the sky. Very often we have wondered about the forces which are responsible for holding these celestial objects in the sky and for their motion in the sky. Hello, in this course we will be learning about planetary motion and the laws which govern it. We will become familiar with the gravitational forces which are responsible for the motion of the planets and their satellites and for the very existence of the universe. We see the sun and the stars rising in the sky every day and then setting again. This observation led Greek philosophers like Ptolemy to conclude that the earth was stationary and it was the center of the universe. Hence, this was called the geocentric model of the universe. According to this model, all celestial objects like the stars, the sun and the planets revolve around the earth in circular paths. For thousands of years, people believed in this model of the universe. In the 16th century, Nicholas Copernicus proposed a model in which the planets moved in circles around a fixed central sun. This was the heliocentric model. Galileo supported this theory after observing the skies with the newly invented telescope. With his telescope, Galileo saw near Jupiter some objects which disappeared for some time and then reappeared again. So he realized that they were going around Jupiter. Galileo had discovered the moons of Jupiter. This observation contradicted the geocentric model. Tycho Brahe was another scientist who spent his entire lifetime recording observations of the planetary motion with his naked eye. Johannes Kepler, his assistant, analyzed the data compiled by Tycho Brahe. This analysis led to the formulation of the three laws of planetary motion. Kepler's first law, which is also called the law of orbits, states that all planets move in elliptical orbits around the sun with the sun at one of the foci. To understand the construction of an ellipse, I have over here an arrangement in which we will construct a ellipse. Here I have this pen and this loop of thread which is fixed at these two ends on this base. Now using this pen, I will make the loop of this thread tight, and keeping the loop of the thread tight, I will move the pen. So you can see that over here on the paper a figure is coming up and it is a figure which will help you understand about the ellipse. So over here you can see that we have got a oval shape. This is the ellipse we were talking about. Now if I bring the ends of the loop close together and again construct the ellipse, you can see how the shape comes out, and the difference between this ellipse and the earlier ellipse is quite prominent. Now you can see that over here the fixed ends of the loop have been brought closer to each other, and Again, we are going to construct the ellipse using the same method, and keeping the thread tight, I again move the pen over this paper and let us see what kind of a loop do we get. So over here you can see that we are again getting some kind of a figure on the paper. Do you see that we have got a figure over here which is slightly different from the earlier figure? Can you spot the difference between the two? Look at it carefully. So over here, do you see that these two figures are slightly different? Yes, you're right. This one, the earlier one which we made, is more oval, while the second one is looking more circular. The reason is that the first ellipse we see has a larger eccentricity, and this one has got a smaller eccentricity. The fixed points over here of the loop on the base are the foci of the ellipse. These 2 points are the foci of the ellipse, and over here these two are the foci of this ellipse. In this figure of the ellipse, F and F dash are the foci. A is the semi-major axis and B is the semi-minor axis. The eccentricity is the ratio of the distance from the center to the foci and the semi-major axis A. If the eccentricity is 0, the ellipse will become a circle and the two foci will coincide. The eccentricity of planetary orbits is very close to 0. The eccentricity of Earth is only 0.0167. Hence, the orbit is nearly circular. But the eccentricity of the orbit of Halley's comet is very close to 1. So, it has a very oval orbit. Kepler found that the planets move fastest when they are closest to the sun, which is called the perihelion distance, and move slowest when they are farthest from the sun, which is the aphelion distance. This arrangement over here which I have will show this particular fact. Here I have a deep dish, and over this dish I have put a cloth. Now, to simulate the sun, I have this ball which I am going to put over here. The depression which is caused on this cloth is simulating the gravitational force of the sun. As the planets, I have these small balls. Now, if I move this ball over the cloth, you see what happens. Do you see that the speed of the smaller ball is lesser when it is away from the red ball, and it becomes larger when it comes near the red ball? Let me do this again for you. So, notice carefully. Do you see and do you notice the difference in the speeds of this smaller ball as it comes closer to the sun? Kepler's second law of planetary motion explains this fact. This law is also called the law of areas. This law states that the line joining the sun and the planet sweeps equal areas in equal intervals of time. The aerial velocity of the planet is constant. This law of areas is a direct consequence of the fact that gravitational forces are central forces. This means that during the orbit of the planets around the sun, the gravitational force of attraction acts along the line joining the sun and the planets. So, the torque experienced by the planet is zero and the angular momentum of the planet about the sun is conserved. Kepler's third law of planetary motion states that the square of the time period of revolution of a planet is proportional to the cube of the semi-major axis of the ellipse traced out by the planet. This law is also called the law of periods. In this table here, we check the validity of Kepler's law of periods for all the planets of the solar system. We can see an interesting result from the table. If the orbital radii of the planets is measured in astronomical unit, which is the distance of the earth from the sun, and their orbital periods is measured in earth years, the ratio of the square of time period of the planets and the cube of their orbital radius comes out to be nearly 1 for all the planets. Sir Isaac Newton made a breakthrough when he realized that the reason why an apple falls towards the ground is the same reason why the moon orbits around the earth. Newton calculated the centripetal acceleration of the moon as 0.0027 meter per second square. The orbital period of the moon and the orbital radius of the moon were known at that time. He then compared the acceleration of the apple and the moon and related this to the distance from the center of the earth. From this analysis, he found that the gravitational force was inversely dependent on the square of the distance between the masses exerting the force on each other. This analysis led to the formulation of Newton's universal law of gravitation. Universal law of gravitation states that every particle in the universe attracts every other particle with a force along a line joining them. This force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. The proportionality constant is called the universal gravitational constant, whose value is constant everywhere in the universe. The gravitational force acting on mass m1 is equal and opposite to the gravitational force acting on mass m2. This means that the force with which the earth attracts the apple is equal to the force with which the apple attracts the earth. We see objects falling towards the earth every day, but the fact that every object attracts every other object eludes us. We never see the tables and the chairs and other objects moving towards each other. The reason for this is the very small value of universal gravitational constant, which is of the order of 10 to the power of minus 11. Objects which fall towards the earth experience the huge mass of the earth, which is of the order of 10 to the power of 24. So the force experienced by the small object causes an acceleration which we can see. Newton's law of gravitation talks about the force between two particles. But what happens if the number of particles is greater than 2? Can we find the force on a particle due to many other particles? Yes, we can do this with the help of the principle of superposition. If we have a collection of point masses, the force on any one of them is the vector sum of the gravitational forces exerted by the other point masses. In the situations shown here, we can see that the force on the mass at the center of the circle depends on the angle between the individual forces. If this angle is 180 degree, this force is minimum. But if this angle is 0, the net force on the central mass becomes maximum. So, in this module, we have learnt about Kepler's laws of planetary motion and introduced you to the law of gravitation, which is given by Sir Isaac Newton. Thank you.